Hello everyone, I'm Yi Xiao from Chongqing University. It's my pleasure to introduce our work, Demonstration 3, towards more practical log parsing with large language models. This work is jointly completed by Yi Xiao, Van Hong Li, and Hongyu Zhang. The rich information included in log data enables a variety of software reliability management tasks, such as detecting system anomalies, ensuring application security, and diagnosing errors. To enable automated log analytics, log parsing is the first and foremost step. Each log message is printed by a logging statement in the source code and records a specific system event with its header and content. The goal of log parsing is to convert each log message into a specific log template and extract the corresponding parameters. Previous research designs a method to automatically generate regular expressions based on source code to perform log parsing. However, the source code is generally inaccessible during system maintenance. Consequently, a variety of syntax-based log parsers without requiring access to the source code have been proposed. These log parsers assume that log templates inherit some common patterns which emerge constantly across the entire log dataset. However, these methods heavily rely on handcrafted rules and domain knowledge. To overcome the limitations of syntax-based parsers, many semantics-based parsers have been proposed. Existing semantics-based parsers can be divided into three categories: training from scratch, fine-tuning pre-training models, and the LM-based log parsing. UniParser trained a deep learning model from scratch. LogPPT fine-tuned the pre-trained language model, Roberta, for log parsing. Although effective, these semantic-based log parsers require certain training overheads, such as training models from scratch or fine-tuning pre-trained language models with label data, which is costly to obtain. Selecting even a few demonstrations can quickly become more laborious as the value and format of logs rapidly change. More importantly, selecting in-context demonstrations can be challenging as the quality of these demonstrations directly affect LM-based log parsing. As is shown in our motivation example, as we change the demonstration for a single query, the results will change accordingly, indicating the sensitivity of demonstrations to the performance of LM-based log parsing. What's more demonstration examples will lead to higher cost and carbon footprint. This raises a concern about whether we need to add demonstrations for log parsing. To overcome the limitations of existing LM-based log parsers, we propose LogBatcher, a lower demonstration-free, training-free, and cost-effective LM-based log parser. The main idea behind LogBatcher is that log data possesses latent characteristics, for example, commonality and variability, which allow LLMs to perform log parsing without demonstrations. LogBatcher contains three main components: partitioning, caching, and batching query. The first component of LogBatcher is partitioning, which is crucial for the subsequent in-context learning process, as it allows large language models to learn the commonalities within log data and associate them with the log parsing task. For every coming log, we first tokenize and clean it, then we employ TF-IDF for vectorization, and DB scan for clustering. Parsing all arriving logs with large language models is impractical due to the high cost, so we leverage a simple caching mechanism to store previous parsed log templates and match them with logs in the current partition. Especially, before parsing, we filter out logs that can be matched with the cache. For those unmatched logs, we process them with large language models, adding the newly generated template into the cache. Logs that belong to the same template might not share frequently occurring tokens, but also exhibit rich variability in their dynamic parts. We propose a batching querying approach to provide large language models with commonalities and variabilities within input logs for demonstration-free log parsing. Firstly, we sample a set of logs from each partition to form an input batch for large language models. A common in-context learning paradigm consists of three parts: instruction, demonstration, and query. Since our method is demonstration-free, our prompt consists only of an instruction and a queried log batch. The output from a large language model may contain redundant information beyond the desired template, so we need a post-process step to locate the template and replace the variables with placeholders more accurately. Sometimes logs that belong to different clusters are mistakenly grouped into the same cluster. We design a matching pruning process. First, we use the generated template to match all logs from the same cluster. The matched logs are considered successfully parsed, and the unmatched logs are then pruned and sent to a new cluster, which will reenter the queue sequence for further parsing. We evaluate log batcher on two public available datasets. These datasets cover logs from distributed systems, standalone software, supercomputers, PC operating systems, mobile systems, microservers, and so on. LogHub2K contains 16 datasets and 2,000 logs per dataset, while LogHub 2.0 contains 14 datasets and over 3 million logs per dataset. We compare log batcher with 4 SOTA unsupervised data-driven log parsers and 2 LM-based supervised log parsers. To ensure more comprehensive comparison, we adopt 3 widely used metrics to evaluate the effectiveness of our method: group accuracy, message level accuracy, and edit distance. The experimental results show that log batcher significantly outperforms other unsupervised log parsers, exceeding the highest GA, MLA, and ED of these methods by 9.1%, 36%, and 4.8% on average. Compared to supervised methods, log batcher still achieves the best GA and MLA, showing that log batcher is effective for the log parsing task. Log batcher aims to support a wide range of log data from various systems. The accuracy distribution results show that log batcher is robust and can be applied to various log datasets effectively. In recent work, LM-based parsers have concentrated on selecting suitable demonstrations for the query, which has led to demonstrations being significantly longer than the query itself. Conversely, our approach improves the efficiency of using large language models by adding more diverse logs to the query through batch prompting. In terms of total token consumption and average token consumption per invocation, our method achieves the best results on most datasets, showing that log batcher is more efficient than other LM-based passes. Log-batcher contains three modules: partitioning, caching, and batching. The ablation study shows that removing any one of them will degrade the performance. Although log-batcher is demonstration-free, it still supports demonstration for more accurate parsing. Compared to Linux, the performance of log-batcher remains stable and high across different numbers of demonstrations. We also researched on the most suitable setting for log-batcher. For example, we found that dbScan performed the best among all clustering methods, likely because it identifies noisy data, which aligns with the uneven distribution characteristic of log data. Meanwhile, we evaluate the impact of different sampling, different batching size, and different LM selection. In addition to evaluate on the small dataset, we also evaluate on bigger dataset. These experimental results are consistent with those on the large-scale datasets, indicating that our method generally incurs less overhead, achieves higher efficiency, and performs better overall. Log parsing is the first and foremost step to enable automated log analytics. We propose log-batcher, a new unsupervised LM-based approach for log parsing. Log-batcher leverages latent characteristics of log data and reduces LM inference overhead by batching a group of logs. The results of our extensive experiments on the two public datasets show that log-batcher is effective and efficient for log parsing. We believe that our method can potentially make LM-based log parsing more practical. Also, we make log-batcher artifacts available and reusable. You can access log-batcher in our GitHub homepage. That's all. Thank you.